right, so as we're getting started today, I want to remind you about the binomial distribution. The binomial distribution is a distribution for a discrete random variable. A discrete random variable is one that can only take on a countable number of values, like 0, 1, 2, 3, 4. It can't be 3.14, right? It's got to be a discrete number of different values. And specifically, a binomial distribution is one that is the sum of the number of successes from several Bernoulli trials. A Bernoulli trial is a process that either results in a success or a failure. So like, it's easy for me to come up with examples from sports. Like one example of a Bernoulli trial is like you step up to shoot a free throw. When you step up to shoot a free throw, you either make the basket or you don't. You either have a success or a failure. That's one Bernoulli trial. So if you repeat this process and you try to attempt 10 free throws and you count the number that you make, the number out of 10 is a binomially distributed random variable. There's only a discrete number of possibilities, 0 through 10, and we're going to be able to assign a probability to each one using the binomial distribution. If I want to ask you about the mean of a binomial distribution, that is the number of attempts times the probability of success for each trial. So n is the number of Bernoulli trials, and p is the probability of success for each trial. And to get the mean is just n times p. The variance is n times p times 1 minus p. And the standard deviation is just the square root of variance. So the standard deviation is just going to be the square root of n times p times 1 minus p. If you love statistics, you can always take a class here called mathematical statistics, and we would actually go through the explanation for why the variance is n times p times 1 minus p, but this is just an intro class, so we're just going to learn the formulas and then we're going to use them. We're not going to discuss why here. So you guys know this already, but the binomial distribution is not the same as the normal distribution. A normal random variable is a continuous random variable, so it can take on all sorts of values in between the whole numbers. And plus, you also know that the binomial distribution has a particular PMF formula and a particular CDF table. The normal distribution has a particular CDF table that's different than a quantile function table. So they have different probabilities. These are not the same distributions, but today we're interested in the scenarios where the normal distribution makes a good approximation of the binomial distribution. So even though these distributions are different, there is a particular case in which the normal distribution looks a lot like the binomial distribution. And so this is what we're going to do today. We are going to take a binomially distributed random variable. We're going to calculate the mean, n times p. We're going to calculate the variance, n times p times 1 minus p. And then if my variance is greater than 10, then it turns out that the normal distribution looks really, really close, really similar to the binomial distribution. And again, if this was mathematical statistics, we would actually prove that this is true in the limit. But since this is not a mathematical statistics class, I'm just going to show you a picture. In red I have a binomial distribution. Okay? If I only look at the red, you can tell that this is a discrete distribution because of the little flat tops. Like, this is telling me the probability for getting a 1, this is telling me the probability for getting a 2, this is telling me the probability for getting a 3, and it looks blocky because it's a discrete distribution. If I put this blue curve on here, the blue curve is a normal distribution. It's bell-shaped, it's symmetric, it's a nice normal distribution. Whenever I put these together, you can see that, I don't know, in certain cases, if my sample size is pretty small and my probability is not very close to half, like the normal distribution isn't really that close to what the binomial distribution looks like. But if I get a situation where my probability is getting pretty close to 1/2 and my n is pretty large, my sample size is pretty large, now it works really well. Right, now the normal distribution curve matches the center of those little binomial distribution probabilities just about exactly. And so this is the situation we're talking about today. We are interested in those times when the normal distribution makes a good approximation of the binomial distribution. And the way we determine this is we say, we're going to calculate the variance, which is n times p times 1 minus p, and if that's greater than 10, we're going to say, yeah, it's close enough. The normal distribution looks like the binomial. But if the variance, n times p times 1 minus p, is less than 10, then we say, no, it's not really good enough. We can't use the normal. We're going to have to stick to our binomial formulas. So, exercise 2 says, determine whether the following binomial scenario can be adequately modeled using the normal probability distribution. It says, you go down to the basketball court to practice shooting free throws. After every attempt, you record in your notebook whether or not you made a basket. After 10 attempts, you count the number of successful baskets. Assume your probability of making each individual basket is 0.55. So that's my P, that's my probability of each success. What's my N? 10 attempts, 10 Bernoulli trials. So my mean of this binomial distribution is N times P, which is going to be 5.5. My variance of this binomial distribution is going to be N times P times 1 minus P, which is going to be 5.5 times 1 minus 0.55. In other words, 5.5 times 0.45. Which is 2.475. All right, so according to our criterion that we just talked about, is this binomial distribution close enough to the normal distribution or not? The question is, can this scenario be adequately modeled using the normal distribution? Yes or no? No. No. Because this number is less than 10. And if this number is less than 10, we cannot use the normal distribution as a probability model. Yeah?
Why is a 10 the deciding factor? Is that because it's n? Or
That is a good question. And again, if you were going to stick around and take my mathematical statistics class, I would be happy to spend a lecture explaining that, right? That's something for like upper division math.
So if it was on the test, would it be 10? Or like, how do we know that?
Oh, if it was like exactly 10?
Well, like, you don't
It was like kind of on the fence. It kind of looks good enough, kind of doesn't. Yeah, it's always 10. It's always the number 10. And really the answer is it's like a rule of thumb thing, right? Like, is there that much of a difference between 9.99 and 10.01? No, there's practically no difference at all. But you have to put a threshold somewhere. You have to decide yes or no at some point. And so people choose 10 because it seems like a good threshold. And you know, we could talk about why is the variance a good indicator? Why did we choose 10 as a threshold? Those are good questions for a different class, but not for this class. We got to draw the line somewhere in terms of how we use our class time. But 10 is just the accepted threshold for reasons. Okay, do another one. Determine whether the following binomial scenario can be adequately modeled using the normal probability distribution. It says, as a student success coach, so all of you guys probably know Lee or Sienna at the Student Success Center. Let's say that they follow 300 students throughout their fall semester at MNU. And the probability of any individual student dropping out during the semester is 0.1. So this is a binomial distribution. The number of students that drop out is a binomial random variable. Each student represents a Bernoulli trial. Either they're going to succeed in finishing out the semester and remain enrolled, or they're not. And each student has this, probability that they're going to be leaving MNU or whatever. And so we can treat this like a binomial distribution. And the question is, we know this is a binomial distribution, but could we adequately model it using a normal distribution? So we first want to calculate the mean, which is n times p. What is n? 300. What is p? 0.1. So that's going to be 30. And then I want the variance, which is n times p times 1 minus p, which is going to be 30 times 0.9, which is 27. So, you tell me, can we adequately model this scenario using a normal distribution? Yeah. Because this number is greater than 10, we can use a normal distribution to approximate that. So if I go back to Desmos, I set n is equal to 300, p is equal to 0.1. I don't know what happened to my binomial curve. Oh, I know what happened. And honestly, not only is this an interesting thing to point out math-wise, the reason that my red binomial distribution doesn't show up when I type in n is equal to 300 here is because Desmos is trying to calculate 300 factorial, which is a huge number, right? That's 300 times 299 times 298 times 297 and on and on. That number is bigger than you can store in the IEEE data type, double precision data type. So it breaks down. It gives an overflow error if you've ever done that in your calculator. So Desmos won't render the red binomial distribution, but if it did, it would look a lot like this normal distribution. And this is actually exactly why we're interested in this. If you're like wondering from a practical scenario, why would anybody care to approximate a binomial distribution with a normal distribution? Why don't we just use the binomial distribution, the exact distribution every time? Well, actually, the binomial distribution is really computationally intensive, very heavy in terms of the numbers that you got to crunch. And so the normal distribution is easier on the computers. Takes up less processing power. So that's one reason among others. But if you could see it, it would be a good match. Okay, what does this say? We say that the result of a binomial experiment is unusual. So there's a vocabulary word. We say that it's unusual as a result if it falls outside of the interval that contains the 95% most likely outcomes. 95% of the most likely outcomes. And I can tell you that for a normal distribution, 95% of the most likely outcomes are going to fall within an interval containing the mean. And it goes from the mean minus 1.96 standard deviations, and it goes up to the mean plus 1.96 standard deviations. So you know my bell curve? It is symmetric about the mean, and so if I want the most likely outcomes, we're talking about the places that the bell curve is the tallest. And if I only want 95% of the outcomes, I'm going to shade a 95% of the area, symmetric about the mean. And that just means that right here, that's negative 1.96 standard deviations, and this is positive 1.96 standard deviations, right? So that this area is 0.95. So I can give you a question like exercise 4 here, and I could ask you, determine whether the outcome described below is unusual.
Is this supposed to be 95 or 96?
1.96. That's the number. Yep, I can show you somehow. You know, the standard normal distribution probability density function has this formula, which you don't need to know, but that's how I can get my standard normal distribution. And if I want to know how to get exactly 95% of the area, what I would want to do is say, I want this green shaded area. And the green shaded area between negative 1.96 and positive 1.96 is exactly 0.95. 0, blah, blah, blah. But it's really close to 95%, right? So that's why we use the numbers negative and positive 1.96. Okay, so exercise 4 says, overall, the incident rate of autism is 1.5%. That means every person born has a 1.5% chance of being diagnosed with autism eventually. A public health expert browses through the data from a city in Kansas with 10,000 children ages 5 through 15. Records indicate that 106 of these children have been diagnosed with autism. So, I know that overall, the probability that any particular child has autism is going to be 0.015. What is my N? Yeah, this is 10,000. Because once again, this is a binomial random variable. The number of children that are diagnosed with autism is a binomial random variable. It's going to sound kind of silly to say this out loud, when we talk about Bernoulli trials, because a Bernoulli trial either results in like a success or a failure. But statisticians don't use the word success and failure the way that regular people do. In this case, each one of those children represents a Bernoulli trial. And when you go to find out, has the child ever been diagnosed with autism, you're talking about, yes, they have a diagnosis as being a success in the terminology of Bernoulli trials, and no, they don't have a diagnosis as being like a zero, a failure in terms of the Bernoulli trial. But what that means is the number of children out of this sample that have an autism diagnosis would be a binomially distributed random variable. And so what we want to verify first is, could I use a normal distribution to adequately model this? And so I'm going to calculate the mean, which is n times p, and that's 1, 2, 3, 4 zeros. So I'm going to move the decimal 1, 2, 3, 4. I think the mean is 1,500. No, 150, right? 1, 2, 3, 4. Yeah, 150. So kind of the expected value. If we were just walking into this with no other information besides this here, I would think out of 10,000 kids, knowing that the incidence rate is 1.5%, I'm kind of expecting that out of 10,000 we would find 150 diagnoses. That's my baseline expectation. And so I find that 106 students have a diagnosis, not 150. That's not exactly 150, but you also have to apply this kind of randomness reasoning to it. If we came across 149 kids with a diagnosis, I wouldn't think that was unusual, because 149 is pretty close to what I was expecting. If I found that only 3 children had been diagnosed, well, that would be really unusual, right? We don't even have to do any math to figure out there's something wrong there. But whenever you've got this kind of number in between 3 and 149, then it's like, well, how do we really determine if 106 is that unusual? So then we find the mean, we find the variance. Let's calculate variance. That's n times p times 1 minus p. That's 150 times 1 minus 0.015. Got to use my calculator for that one. That will give me 147.75 for my variance. So can I use a normal distribution here to approximate that? Yes. Because the threshold is 10, right? As long as this number is bigger than 10, then yes, normal is okay. So for a normal distribution, I know that 95% of the most likely outcomes fall inside the interval where I have the mean minus 1.96 standard deviations up to the mean plus 1.96 standard deviations. And also, I need to find what the heck is a standard deviation. Well, the standard deviation is just the square root of the variance. So I need the square root of 147.75. My standard deviation turns out to be 12.16. So the lower bound here is 150 minus 12.16.
How did you get 12.16?
I took the square root of the variance. The standard deviation is always the square root of the variance. And then the mean, oh, I'm not supposed to subtract the standard deviation. I'm supposed to subtract 1.96 times the standard deviation. So let me try that again. I'm going to do 150 minus 1.96 times 12.16. Okay. So now I get 126.2.
Could you say how you did that again to get the 126?
I took the mean, and the mean is 150. So 150 minus 1.96 times 12.16. And then I do 150 plus 1.96 times 12.16. And I get 173.8. So again, knowing that this is a binomial random variable, knowing that the probability is 0.015, and knowing that I'm looking at a data set with 10,000 children, I'm expecting that 150 kids would have an autism diagnosis. But I know it's not going to be exactly 150. Like, it's probably going to be near 150, but maybe not exactly 150 every time. What I do know is that I would expect 95% of the outcomes that happen from this random process to fall somewhere between 126 kids and 173 or 174 kids. So whenever I look at this city and I find out that there's only 106 autism diagnoses, I would think that's unusual. It's pretty unlikely that you would get a number outside of this range. So if you do get a number outside of that range, that's kind of like a red flag. Like, maybe we need to follow up on that. In the practical sense, that wouldn't mean that this city has fewer children with autism. It would more likely indicate that this city is not doing enough autism screenings, right? There's some reason they're not getting enough diagnoses. And so you might look at what kind of resource does this city need? Do they need to have a traveling doctor go to the elementary schools to help with screenings? Do they need to train the diagnostician at the elementary schools to, screen better? I don't know. But I'm not a health person. I'm just a mathematician. So I don't know exactly what you do with this data, but I do know that in public health, they kind of look at this stuff. They look at the rates of diagnoses of different conditions, different diseases in every region, every city. And they kind of look for red herrings like this. They look for unusual results. And once you flag something as, hey, that's a little bit fishy, that's a little bit unusual, then you can do a little bit more expert qualified work in figuring out what's going well, what's not going well. You know, it would be equally unusual if you had too many diagnoses, right? Like if you had 180 diagnoses, that's also unusual.
So then how would you write the answer?
Oh, how do I write your final answer? I would say, determine whether the outcome is described as unusual. I would say yes. This is unusual. Unusual. Because 106 is not in this interval. Good question. Okay. Exercise 6 says, suppose x is a binomial random variable with n is equal to 20 and p is equal to 0.5. Find the probability that x is equal to 12 using the binomial distribution. Okay, we can do that. The probability that x is exactly equal to 12 from the binomial distribution, this is a PMF problem, a probability mass function problem. And we know the probability mass function for a normal distribution is n choose k times p raised to the power k times 1 minus p raised to the power n minus k, right? Here k is 12, because I'm looking for the probability that x is equal to 12. And so this would be n, which is 20. 20 choose 12. And then 20 minus 12 factorial. And then p is 0.5 raised to the power 12. And then 1 minus 0.5 raised to the power 20 minus 12. And you know, you can simplify a little bit. $20 factorial divided by 12 factorial is going to be 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13. And 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2. And then 0.5 to the 12th power times 0.5 to the 8th power is 0.5 to the 20th power. I hate doing factorials. I've got to remind myself not to make such long factorial problems. So the numerator is a huge number. I'm not going to write that down because I'm just going to instead do answer divided by 8, divided by 7, divided by 6, divided by 5, divided by 4, divided by 3, divided by 2. Okay, so the leading up to it part, that whole crazy coefficient is 125,970. And then 0.5 raised to the 20th power is, it's a super tiny number, so I'm not going to write it down. I'm just going to multiply that times the big number. And I get 0.1201 for my probability. So this reminds me, you know, on Friday when we were taking a test, I got so many questions about how to use the calculator. try to iron out those wrinkles before you take the test, right? Like whenever you're looking at your homework and you're studying for your test, actually have the TI-30 with you when you study. Try to work out the problem in the calculator, and if it doesn't work, then like, try to get all those little calculator questions ironed out beforehand, so you don't have to worry about that while you're taking a test. Practice is important. So is the normal distribution a good approximation? Well, that depends on the variance mostly. N is 20, P is 0.5. So N times P is 10. The variance is N times P times 1 minus P, which is going to be 20 times a half times 1 minus a half is still a half. So that's going to be 5. So is that going to make a good normal approximation? No. This is less than 10. So no. Normal is not an adequate approximation. And so whenever I give you this question on the homework, whenever I copy and paste that homework question to a test, I'll try to write the next question where it says find the probability using the normal approximation. I'm going to rewrite it so that it says if the normal distribution is an adequate approximation, then find the probability using the normal approximation. And so we would say this is not adequate. Another thing that we've talked about before in class is like, if I have a continuous random variable, the probability that my outcome will be exactly 12 is actually 0, right? If I were to take a normal distribution and I say, what's the probability I get this particular outcome from my normal distribution at 12? The probability is 0. It's possible. It's within the range of possible outcomes I could get, but there's no probability assigned to it. In continuous random variables, we can only talk about the probabilities between two bounds. Under the normal distribution, we talk about the probabilities as being the area under the curve. So like the probability of getting an outcome between negative 1.6 and negative 0.4 would be the area of this green shaded region. But what happens if I want exactly the outcome negative 1.6? Well, then the lower bound would be negative 1.6, the upper bound would be negative 1.6, and there is no area, right? There's a little bit of area if I create an area by changing the lower bound to be different from the upper bound, but we're talking about a range. If I have exactly an outcome that I'm expecting, the area is 0, the probability is 0. So instead, if I want to use the normal approximation, then we have to say, right here I'm thinking about the binomial distribution, right? If I want x equals 12 in the discrete binomial distribution, using the normal approximation means finding the probability that x is going to fall between 11.5 and 12.5. And if I wanted the probability that x is equal to 13, I would look at the probability between 12.5 and 13.5. So I'm looking at, this chunk of area under the normal distribution that has a width of 1. And so we end up having these rules for like, okay, if I'm using the exact binomial distribution, this is how I would discuss. These are the symbols that I use to represent the probabilities. What if I want to approximate those probabilities using the normal distribution? Well, now I've got to kind of pad all of the edges. All of the lower bounds are going to go down by 1/2. All of the upper bounds are going to go up by 1/2. And that's going to give a little bit of area to the exactly equal to case. And I have to continue that idea for all of these others. Like, if I wanted the probability in the binomial distribution that my random variable is going to be between 2 and 6, including 2 and including 6, then in the normal case, I would want the probability between 1.5 and 6.5 in order for it to be fair between the continuous and the discrete. So that's something to know. Put on your little page for the next test for sure. I'm going to try to show you what that looks like and why. Oh. Okay, so here's my picture. If I want the probability of getting exactly a 22 from the binomial distribution, then I'm talking about this rectangle here. So in red, my binomial distribution, if I want exactly the probability of getting a 22, then that would be the area of this rectangle, okay? What if I've got my normal distribution there, and I want to use the normal distribution to approximate this? Well, I would still use the same width, but I would just calculate this area in here with kind of the slopey blue top. And that area should be pretty close to the area I get from the binomial distribution. There's going to be a little bit of a difference because it's not exact. This is an approximation, but we hope it's close enough. And that's why we got to give a little bit of width to it. That's where this table comes from. All right, so we'll do a few more of these examples here in the next 20 minutes. See how much progress we can make. 100 students attempt to kick a field goal at the football field. For every student, assume a probability of success of 0.2. What is the probability that exactly 25 students are successful? So we can try to find this probability using the binomial distribution. The probability that exactly 25 students are successful. I can already tell that doing this with the factorials is going to be a nightmare. I'm going to have like 100 factorial. So forget that. I'm going to cheat. And I'm going to use Excel to tell me the number of students I want to succeed is 25. The number of trials is 100. The probability of success for each student is 0.2. And I don't want this to be a cumulative distribution function. I want this to be a probability mass function, so I tell it false. Okay, my probability is 0.04388. Determine whether the normal distribution is a good approximation. And so we're asking, is n times p times 1 minus p greater than 10? I don't know. That's going to be 100 times 0.2 times 0.8 . I got 16. 16 is larger than 10. So the answer is yes. A normal distribution will be an adequate approximation this time. Next, we want to find the probability again using the normal approximation. And I know if I use the normal approximation and I say x has to be exactly equal to 25, that's going to give me a probability of 0. So instead, I try to find the probability that x is between 24.5 and 25.5. And this is a question, we've kind of done something similar before. It's going to be the probability that x is less than or equal to 25.5 minus the probability that x is less than or equal to 24.5. Because the first term is going to give me the probability of all of the outcomes less than or equal to 25.5. And then to narrow this down, I need to subtract away all of those probabilities that are less than or equal to 24.5. I'll only be left with the probability in between 24.5 and 25.5. So now we need the normal CDF, and we have tables for that. But the tables require a z-score. A z-score is what I get when I take the measurement minus the mean divided by the standard deviation. Our mean here is n times p, so the mean is 20. It's 100 times 0.2. The variance here was 16, which means the standard deviation is 4. The standard deviation is always the square root of the variance. So my z-score is going to be whatever I want to in terms of measurement, minus 20 divided by 4. So what about here for 25.5? The z-score would be 25.5 minus 20 divided by 4. And 5.5 divided by 4 is 1.375. To get this z-score, I do 24.5 minus 20 divided by 4. 4.5 divided by 4 is 1.125. So we need the tables. We got to look it up. And it looks like I got to round to 2 decimal places to use the table. So when I round these guys, this thing's going to round to 1.38. This one's going to round to 1.13. Let's look for 1.38 first on the CDF table. There's 1.3. There's 0.08. So it's 0.9162. Then we look for 1.13. There's 1.1, there's 0.03. So that probability is 0.8708. And then I subtract. And we get 0.0454. Which is 4.54%. So one thing we might be interested in is like comparing the two. When I used the exact binomial distribution, my result was 4.388%. When I used the normal approximation, I got 4.54%. So we did not get the same answer when I used the binomial exact distribution versus using the normal distribution approximation of that distribution. But even though it's not exactly the same answer, it's still kind of close. You know, it's still like within like 3 to 5% error. Not terrible. Pretty good. So, any questions about how to do that? Okay, so we've got a bunch of exercises that look like this. We just talked about how to do this, how to take an exact outcome probability from a binomial distribution and add a little bit of padding on either side and use the normal approximation. I'm going to give you other examples in your homework about how to do these other rows on the table, right? Different probabilities from the binomial translates to different probabilities from the normal, but you can use that as a guide, hopefully to figure those things out.